Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to launch your next project, you'll need somewhere to deploy it, so you should check out Linode at dataengineeringpodcast.com/Linode and get a $20 credit to try out their fast and reliable Linux virtual servers for running your data pipelines or trying out the tools you hear about on the show. Go to dataengineeringpodcast.com to subscribe to the show, sign up for the newsletter, read the show notes, and get in touch. You can help support the show by checking out the Patreon page, which is linked from the site. To help other people find the show, you can leave a review on iTunes or Google Play Music, tell your friends and coworkers, and share it on social media. Your host is Tobias Macy, and today I'm interviewing Christopher Meiklejohn about establishing consensus in distributed systems. So, Christopher, could you start by introducing yourself?
Sure. So my name is Christopher Meiklejohn. I'm a PhD student at the Université Catholique de Leuven in Belgium and Instituto Superior Técnico in Portugal. And the area of my PhD research is on programming large-scale, eventually consistent systems, specifically systems that are operating at the edge and mobile systems. So places where you can't really use consensus. And so a lot of my research is in trying to avoid consensus and trying to do things coordination free as possible.
And how did you first get involved in the area of data management?
I've worked in industry for a while. I worked in industry for something like 15, 16 years before I decided to go back and do my PhD. And so my first kind of introduction to distributed systems was when I was an engineer at Basho Technologies working on the React distributed database, which is a NoSQL eventually consistent key value store that's used by a variety of industry folks written in Erlang. And from there, I got involved in European research project on CRDTs and kind of eventual, trying to make working with eventual consistency easier. And I ended up leaving Basho Technologies to go pursue my PhD with the research group that I began working with while I was there. Kind of since then, I've worked on a bunch of different NoSQL databases, and I worked on some distributed programming work with Comcast and Mesosphere, kind of in the interim time between starting my PhD and leaving Basho Technologies.
And as you mentioned, you've spent a decent amount of time working in industry with distributed systems, and you're currently doing research into how to establish consensus in widely distributed systems. And one of the focal points of that research and your experience, from what I was able to gather while doing research for the show, is in the concept of CRDTs. So I'm wondering if you can just start by explaining a bit about what that is and how you first began working with them and some of the current manifestations of them in the, both in academia and in industry.
If you kind of think about the boundaries of the kind of CAP result and the CAP problem, you're kind of left with this choice when building these large scale distributed systems where you know that network partitions are going to happen and you have to either favor consistency or availability. And so in a consistent system, you would want to kind of maintain a total order. You want to ensure that all of the nodes agree kind of in lockstep, and you kind of don't have divergence of values if you're thinking of something like a database. From the availability side of things, you want to keep the system operational at all the time. And so even when the system's partitioned and you can't get consensus, you want the system to be able to continue operating. And so kind of you have these two bounds, this kind of CP area on one side and this AP area on the other side. And so a lot of the CRDT work kind of looks at these kind of global scale systems where, I might have a database copy in Japan, and I might have a copy in Singapore, and a copy in Virginia, and a copy in California. And the problem of consensus becomes harder because inevitably the latency, obviously the latencies are so long because you're sending messages between Japan and California, for instance, or Japan and Virginia, and the latencies being high, partitions also can happen as well. And so kind of at the global scale, and even considering mobile, for instance, where devices are coming and going offline and things like this, you have to deal with these problems of latency and these inevitable network partitions. And so CRDTs kind of come from the angle that you want to stay on the availability side, but if you stay on the availability side and you let nodes kind of continue to operate when they can't talk to all of the other nodes in the system, you might have a system where not everybody agrees on a value at a given time. And so kind of the famous example of this, at least in the literature, is this shopping cart that Amazon talks about when they built their Dynamo database that React and Cassandra are based off of, where, rather than have a system that can't accept somebody adding an item to a cart or removing an item from a cart, they always want to accept the operation. And what ends up happening is that you might have a conflicting add and remove, and you have two copies of the object. And when the user goes to check out, you kind of have to make a decision which one is right. Is the left one right? The one that has the item removed, or is the one that has the item added right? And it's hard without tracking a bunch of additional information. You don't know whether that add came before the remove or after the remove. And in one case, it might result in the item not being there. In another case, it might result in the item being there. And so in Amazon's case, they basically said, well, we'll just, the shopping cart as a set, and we'll take set union because that's well defined. And, this results in these anomalies where things might come back. And so it's kind of this insight that led a bunch of researchers in around 2011-ish, but the work kind of has its genesis back in a paper from 83 where it said, well, this idea that we can have a mathematical function that knows how to resolve these differences in kind of a deterministic way, can we kind of generalize that? Can we build a general theory around that? And so this kind of general theory and this framework for building data abstractions that have these properties is referred to as a CRDT. To make this a bit more straightforward to think about, you can think about it as a data type, like a normal data type, like a set or a dictionary or a counter or a register or Boolean, where you just have that data type, but with an additional merge function. So it says for any two copies of the object, I always have a way to merge them together. And so this allows us to say that if I have a shopping cart that has item A in it on either side of so if I have a shopping cart that can do add and removes and is a CRDT, I can operate on one copy of it, and I might have concurrent changes happening to another copy of it, and I can't get consensus because there's, like, let's say all of the nodes are partitioned from one another. But when the partition heals and the nodes all communicate with one another, I have a way of merging all of those changes together in a way that makes sense. And so kind of the easiest CRDT you can think about is if I have a set where I can never remove values from it, then simply taking the set union is sufficient to merge any copies of this set. And so I can apply changes to one copy over here, one copy over there, and then merge them all together just by taking the union. And that result would be correct, regardless of how the executions are interleaved. And so when things get a bit more complicated when you want to start removing things, because now if I remove something from it, set union is no longer sufficient because a copy that is old or out of date, when merged with a newer copy when the item's been removed, that item will reappear. And so as you want to enable data types that have more operations on them, these merge functions have to get more and more complex, and the amount of metadata you have to store gets more and more complex. And so kind of the CRDT literature basically takes these really simple types, like a set where you can never remove anything, and kind of increasingly makes them more complicated, and gives you richer and richer data types, like a set where you can remove and add things, or an arbitrary number of times, or a dictionary where I can, you know, have a bunch of keys and set the values in the dictionary for those keys and things like that, right? And so the CRDT is kind of a broad term for this collection of data types that have merge functions.
And for a lot of databases that are operating at distributed scale, they generally have the notion of eventual consistency, which is largely what you were talking about, where if there is a network partition, at some point they will reconvene and start to try and migrate data between each other. And in some database systems, for instance, CouchDB, they use sort of optimistic concurrency control where they'll just keep a reference to both versions and they'll just arbitrarily choose, but deterministically, one of the states to be the reality, and then it's up to the programmer to determine the business logic to reconcile those states. And so with a CRDT or conflict-free replicated data type, you're moving some of that business logic into the data type itself as opposed to having it live in the application code to resolve those conflicts. Is that an accurate representation?
If you go back to kind of the earliest work is this paper by D. Parker in 83 on detecting conflicts when you have concurrent modifications without coordination. And this paper is kind of the first place that kind of highlights this problem, but probably the most notable system that talks about this is the Bayou system from Park, which basically says exactly this. It says that you'll have conflicting updates and will call back into user code asking the user to resolve the conflicting updates. They'll have to kind of make a choice, right? And so actually the early versions of React do this. If you have concurrent changes at the same time, when the system resolves them, it will store both values. And so you'll get two objects back instead of one, and then the database expects you to write one value back to the database. And so that's how React worked. And actually, what's interesting is that behavior is actually a CRDT. So the idea that you have a value and it diverges and you create an object with two values in it, and then you resolve that to one is actually a CRDT called the multi-value register. And so that idea actually nicely fits into this CRDT generalization, because the idea that you store both and then resolve it to one that supersedes the previous two isn't itself a CRDT. And so yeah, so React to this day, if you get a default install of the React database, operates precisely like that. It will store both values, it asks the user to resolve. However, React does have a series of data types that you can use if you want that automatic resolution to happen. A lot of systems that are in production have been built. A lot of people create custom CRDTs because they want that kind of custom resolution logic. What's nice about the mathematical framework that CRDTs present is that they have a nice way of knowing whether those merge functions are going to be correct. So they give mathematical properties that this merge function must have for it to be correct in all cases. Where if one person was to just write it kind of an ad hoc merge function, and wrote a merge function for every possible conflict that they would have in their system, inevitably this is usually pretty ad hoc. It's usually pretty error prone, pretty easy to get these, with a sufficiently complicated data type, it's pretty trivial to write an incorrect merge function. And so kind of establishing a base set of CRDTs that map to the data types you'd have in a normal programming language, like a register or Boolean and stuff like that, enables the programmer to work with those and compose those in a way that's safe, that has safe merge functions, rather than kind of writing custom data types with custom merge functions and potentially getting it wrong.
And other than CRDTs, what are some of the other methods for establishing consensus across nodes in a system that have been used in the past and currently? And how does increased scale affect their relative effectiveness and where they break down?
Yeah, so there's kind of an interesting thing here, because CRDTs don't necessarily get you. I mean, if we kind of look at the kind of academic definition of consensus, CRDTs are not going to get you that definition. So that kind of the academic definition of consensus is going to be kind of these three properties of this termination, agreement, and validity, which basically says, like, at the end of the execution will terminate. All of the nodes will agree on a value, and that value is proposed. And so CRDTs don't actually give you that, because the value that you actually might result in, like for instance, if we are operating on the same object and I add 1 to the set and you add 2 to the set, we might ultimately agree on the value where 1, 2 is in the set. So that wasn't actually a value that any of the individual participants proposed, but that's the value that we arrive on. So CRDTs kind of give you this agreement property, but they don't necessarily give you this validity property, which says that the value that is agreed upon was a proposed value. But what they do guarantee is that those changes that all of the individual parties make will be incorporated kind of in that final result. And this is because, with the CRDTs, you're not necessarily getting a total order over the execution. You're getting this partial order over the execution, where traditional consensus would give you kind of this total order over all of the operations. All of the nodes kind of agree on each value as they're being proposed, and come to some final agreement on a value. Now, in terms of mechanisms for achieving consensus, I mean, kind of the gold standard here is Paxos, and kind of all of the subsequent variations of Paxos. And then you have protocols like Raft and protocols like view stamped replication revisited, and things like this, right? And so, kind of in those systems, the way those work is that you will use kind of a ballot proposition mechanism, where somebody will propose a value, and you'll have acceptors or rejectors kind of on those values, and they'll continuously propose ballots until they come to agreement on a value based on majority. And these systems typically require kind of a majority of participants to be online. If they need to be, Byzantine fault tolerant, you need to have more participants online. They usually involve kind of 2 rounds of messages to come to an agreement on something. And these protocols kind of are, you can see this kind of standard technique in things like two-phase commit and stuff like this. Now, these protocols can get very slow when they operate at larger geographic scale. So obviously in the mobile case, you have a problem because if devices are transient, then coming to a majority may be difficult if a majority of those devices are offline at the time. So consensus becomes problematic if you actually want the mobile devices to become participants in the round, if they're all going to be proposing potential values. Now, if you have a geographically distributed data centers across the world, this becomes problematic because you need to wait for round trip messages, typically for these two rounds, to happen between all of the participants that are geographically spread out. And so this protocol can start to slow down when participants are further away. Partitions become more problematic. And things that try to mitigate, things like Spanner and systems like Calvin or whatever, databases like Calvin, databases like Spanner, try to mitigate these things by using clever techniques, by, electing sequencers and then having deterministic dissemination of events downstream, like deterministic effects. Some of the, Spanner has this true time mechanism that uses synchronized clocks via GPS receivers and atomic clocks to try to approximate windows of windows of vulnerability between the transaction commit period. So all of these mechanisms are trying to kind of, I kind of think of it as just like there's this kind of this bound that you're just trying to get between, trying to optimize for, right? And so there's all these various different versions of Paxos that try to do different things to get around this fundamental problem that ultimately you have to talk to the participants, and the further away the participants are, the longer it's going to take, right? And so some of these variants try to leverage commutative operations, so some things can be done out of order and try to game the system that way, and some try to use these atomic clocks to kind of optimize that way. And so it's all just this game to try to hide the latency. You have to pay the latency somewhere, because you have to talk to the node, you have to send it a message. And so the question is, where can you hide that latency in the protocol? And different protocols optimize for different use cases.
And one of the projects that you've been involved in to try and make it easier for engineers to build systems that are capable of these large scale and massively distributed scale systems is the LASP project, which also relies on CRDTs and some of its layers. So I'm wondering if you can just describe a bit about what LASP is and what your role in the project has been.
Sure. So LASP is basically my PhD work. I started it in, I think, 2014, and I've been working on it basically every day since then. And so what it basically is trying to do is think about using CRDTs outside of the database. And so it's a data flow programming language, so it would look like something like Google Dataflow or RX or something like Naiad or TensorFlow. It looks similar in it being a data flow language, and it's for writing computations with CRDTs. And so the language is super restrictive. There's not a lot you can do in it at the moment, but all of the programs that you can write in the language are guaranteed to be safe for deployment on any topology. So it assumes it makes no assumptions about ordering or anything like that. The only data abstraction in the language is a CRDT. And so what that basically means is that events can disseminate through the network in any order, and it doesn't change the outcome of the program. So a program is completely safe to run on an edge network with sensors. It's safe to run on a mobile network. It's safe to run in the data center. It's safe to run across data centers. And so what the work we've been doing over the past years is trying to make that language more expressive. So add more things in it. So right now it's kind of programs can only be directed graphs. You can't have cycles. You only can do kind of basic data transformations and some small amount of aggregations right now. It's sufficient to express some subset of SQL, so it's been useful for writing programs that kind of have that data access pattern. But what we'd like to do is kind of grow it into a richer program, a richer kind of functional style programming language. And so we've been working on that. And kind of along the road, it's been, just a lot of implementation and experimentation and trying to figure out kind of what we can build with this. And so from the academic side of things, LASP is kind of a formal semantics for a programming language, but from the implementation side of things, it has grown to be quite a large code base now. It's a collection of a reference implementation of every CRDT that's come out of our group. So we have a reference implementation of I think at least 30 different data types in Erlang. In addition to that, it's a lightweight programming layer on top of a peer-to-peer replicated database, which is the storage layer for the CRDTs that the programming language uses. And then that peer-to-peer database, to scale it to the number of nodes that we want, we scaled it up to about 1,000 nodes last year, and this year into next year, we're hoping to get to 4,000 nodes. In terms of that, we had to write an entire distribution layer from scratch because we couldn't rely on Erlang. So now we have this entire distribution layer that's written from scratch. It runs in various topologies. It supports writing distributed Erlang applications that operate either in full connectivity, client server, peer-to-peer, all sorts of stuff like that. And then to evaluate this at scale, we actually ran a series of experiments on Google Cloud Platform and Amazon. We built an entire deployment infrastructure for it that allows us to deploy these Erlang applications there via Docker or, through Kubernetes and stuff like this. And then it uses our distribution layer for messaging between all of the nodes. So LastPass, started off as this really small programming layer, sort of formal semantics, and now it's kind of this full stack distribution thing. And what's been really nice about it is we've seen a bunch of adoption of the individual components. So our data storage layer and part of the programming model is used by this project called Orleans, which is a port of the Microsoft Orleans programming framework to Erlang. We have a couple other industry users that haven't gone public yet, so I can't name them, but that are using our distribution layer to get around problems that they ran into in the standard Erlang distribution layer. And we've seen some other adopters of the data types. So the artifacts that we've constructed during the project have made their way out into industry. So that has been a kind of a nice reinforcement that our work has been valuable.
I can imagine that must feel pretty good, seeing that people are actually starting to leverage your system even before it's necessarily been marked as sort of general availability or production ready by people. So people are willing to experiment with it, and there's enough stability and usefulness in it that they're able to actually start building their own systems.
Yeah, for sure. It's been really nice to have people reach out to us and to see, come across a project in the wild that's using part of the stuff that you made as your PhD is kind of a nice feeling. So
And in the process of your research and your work on LASP and your work in industry, what have been some of the most challenging aspects of working with CRDTs and distributed consensus protocols, to both just from the aspect of being able to understand the operations that are at play as well as actually implementation level details?
I think the hardest part, the CRDT stuff, that's kind of our primary area. That's where all our expertise in. So that's actually been the least problematic. I think the most problematic has been, or the most challenging, I think, has been trying to just run experiments with this stuff and kind of see. It's really hard to run large scale experiments on kind of public infrastructure and draw conclusions from it, just because of the variability of stuff. To kind of give you an idea of this, we can run some of our experiments that we ran, we want to simulate things and we want to run on like 2,000 3,000 nodes or something like this to run an experiment. Getting 3,000 instances to run an experiment on Amazon is difficult to do, and then it's difficult to keep all of those instances running. And even if you sub virtualize them, which we do to run them, to save costs, it's difficult to keep everything running. It's difficult to know if things are working correctly. And then just because kind of the non-determinism that's inherent in the networks that these cloud providers have, you can run one experiment now and we could run the same experiment tomorrow morning and we could see completely different results. And so when you're doing this CRDT work, you design a data structure with a particular like space or time complexity locally, and then you test it out and you see that behavior works. But then when you want to run it on a real network, let's say you get a workload from Facebook or something like this, or whoever, Google, you download some workload that's available for academic use, and then you want to run a workload with this. The workload has very particular characteristics, and some of these workloads need to be run on fairly beefy hardware if you want them to be representative, and it's really difficult to kind of draw conclusions. And so kind of, I think one of the big problems with kind of experimental science around like large scale cloud applications today is that anything that's kind of done over 1,000 nodes at this point is done in simulators. And simulators, at least a lot of kind of the state of the art simulators that we have in the academic space for doing this stuff kind of gloss over some of the low level implementation details, right? A simulator is going to be a lot different than a real TCP stack running a particular version of the Linux kernel or something like that. And so it's hard because, at least from my experience in Basho, what we found was that taking CRDTs out of an academic context where they had a particular performance profile and putting them in a real database with real users, you see a completely different performance profile. And so ultimately, we want to have adoption of these things, but we have to meet somewhere in the middle, right? We can't rely on academics to build production quality code. That's not what they're paid to do. That's not what they should do. They should be doing research. But we want there to be something that industry folks can take and actually work with, and so we need that gap to be as small as possible. And we're, at least with our work, what we're trying to do is build Erlang stuff that might not be bulletproof. It might not be ready to go into a bank, but it's at least good enough for some startup to use or something like that, right? So we're trying to get our stuff as close as possible to where somebody can pick it up and run a real workload on it, and then hopefully will come back to us and say, this is what we saw. Can you find a way to fix this? And that would be nice to have that kind of feedback loop, because you don't want to do research on some idea that is never going to be looked at, or is going to disappear into some paper archive somewhere. You want to do research on things that really matter and things that people can use. And so kind of that's kind of been the real challenging part, is trying to kind of bridge that gap, trying to close that gap as much as possible. And I think we're getting there. I think as we get more users and kind of show off what we can do, and build demos and things like this and talk about our stuff a lot, I think we'll get there, but it's not an easy challenge, let's say.
And for people who are working in industry that want to take advantage of some of the concepts behind CRDTs and their capabilities, are there any sort of applications that are available off the shelf, or tooling that's available off the shelf to assist in implementing those CRDTs or using pre-built CRDTs? And what are some of the complexities or challenges that they should be keeping an eye out for while they're working on that?
Yeah, so I mean, recently there's been a bunch of CRDT stuff that's been kind of happening in industry. I mean, at least I'll highlight, like, I think a few things. So GitHub and some folks at GitHub have a CRDT library with some data types. I don't remember the name of it offhand, but I can try to get that for the show notes. But it's the basis for their collaborative editing extension for their editor, the Atom editor. And then there's a group working on something called Auto Merge, where they've Martin Kleppman and a few others who have built a JSON CRDT for use in JavaScript applications with an implementation. So you have a JSON object, you can store whatever in it, and you can, it has a merge function, you can synchronize it, and all sorts of stuff like that. So that's probably what I would recommend a lot of people kind of start with, because it's a familiar data structure, it's JSON, and it has merge semantics, and they have a nice kind of library that you can just use with NPM to start playing around with stuff. So that's one that's really kind of, I think that's one of the ones I know of that's probably the closest to uh, being something that somebody could just pick up and start using today. At least from the Erlang side of things, we have a library that's, our CRDT library is probably the most robust library that we have out of our academic artifacts. And so there's a library called types under the LASP organization on GitHub that has an implementation of a variety of different data types in I think it's like 30 data types in 2 different flavors that people, at least in the Erlang community, have started using. I think Mesosphere was using it at one point, and there were a couple other people I think that were as well. And then, at least from the Java side of things, Akka has a CRDT implementation as well that was written by the guys over there that it's pretty up to date with at least I think the paper from last year on Delta CRDT. So that's pretty up to date as well. So I think those are probably the good implementations to look at if you're looking at implementations of the data types. In terms of database work, we have a database that is called Antidote. So we have a database called LASP-KV, which is kind of the data stored that's embedded in LASP that can be used to be embedded inside of Erlang applications. So we have an embeddable peer-to-peer CRDT data store in LASP that you can use, which is the one that Orleans is using. And then we have a database called Antidote, which is a standalone database as opposed to an embeddable one that is a CRDT database with transactions that came out of our research group. It is not kind of industry grade yet, but you can download it as a Docker image. You can boot it right up and start playing around with it. So that's another way if you want to kind of look at it from a database perspective. And then, at least in terms of databases that support CRDTs, React is kind of the primary one that has a whole collection of CRDTs built into it that you can use that me and a bunch of the other Basho engineers worked on.
And for people who are working with some of the sort of big name data engineering tools like Spark or Flink or some of the different streaming solutions or even Hadoop and doing MapReduce jobs, are there existing tools or support within those tools for being able to leverage CRDTs?
I'm not really sure. That's a good question. I mean, at least from the Spark side of things and the Hadoop side of things, that processing is kind of, I mean, from the Hadoop side of things, you're usually processing immutable data, so there would be no need for CRDTs there. But I imagine you could leverage CRDTs in Spark if you'd like to, using the Akka library, considering the Akka library is written in Scala. So I imagine you could use that, but I don't know of like anything that's really integrated with those products.
And going back to Antidote DB, you mentioned that it's not quite sort of industrial grade yet, but that it's available for people to experiment with and play around with. So, what's your vision for that project, and what are some of the particular use cases that you think it's well suited for?
Yeah, so Antidote DB is trying to solve kind of is kind of trying to be like kind of the spiritual successor to systems like React and academic systems like COPS and General Rain. And basically, what it's trying to do is React provides eventual consistency, where Antidote provides causal consistency. So with causal consistency, you get stronger guarantees than you get in eventual. You'll get guarantees that if a particular client does A and then does B, those results will become visible A and then B, rather than in eventual consistency where B may become visible before A. And so that's nice because that matches well to writing programs that are sequential. So if you're writing a sequential program and let's say you want to write an object to the database, and then you want to add that object to an index, under eventual consistency, you can run into anomalies where the index might point to an object that's not there yet, where under causal consistency that can't happen. The other nice feature that Antidote provides is transactions. So it has a transaction facility, so you can do updates together, which is something that React, for instance, can't do. So that's nice for grouping updates that need to happen together in a batch. Now, what we're working on adding to Antidote now is ACID transactions. So Antidote is kind of the product for the vision that we have called just right consistency. And what just right consistency argues is that using consensus and coordinating for everything is too much, because there's only a subset of operations that you actually need to coordinate for to prevent seeing incorrect states in your application. And so by having causality and transactions, these things are always available. You don't need to coordinate for them. And they guarantee that things can happen in batches and things happen in order. Well, they happen in some order. They happen in a kind of like an order if then else, kind of like a order. And then the only things you actually need to coordinate for or get consensus for are things where you have to check something and take an action based on that. Because under eventual consistency, you might check something and then it might change before you take the action. And so the kind of the antidote vision is only coordinate for those operations. And so, the obvious thing to attack with this design philosophy is, how do I know what the things I have to coordinate for are, right? So the spanner approach is coordinate for everything, you don't have to think about it. The antidote approach is coordinate only when you need to, and then now you have to figure out when you need to. And so kind of the complementary to this database is a static analysis technique that is being developed and hoped to be industrialized, that basically uses annotations that are done in your source code to determine exactly which operations require coordination based on kind of a first order logic. And then what you can do is basically run an analysis of your program, and it will tell you exactly the points where it needs to insert coordination and only coordinate there. And so that's kind of the vision for the product. We're not there yet. So we have a database that has transactions, it has causal consistency. And so, we need to get the ACID transactions in there. We need to then kind of refine this static analysis technique, and then you'll kind of have this comprehensive story of coordinate only where necessary and pay and get the benefits of eventual consistency, causal consistency where you can.
And you're working in academia now, so I'm wondering if there are any particular areas of research that you've come across that you're most excited about seeing further development on and or seeing them bridge the gap to being used in industry.
So I think the area I'm in, I think is really great. I mean, not specifically my thesis, but the kind of the general area of trying to take. So when I look at systems like LASP is a system about programming with CRDTs, where we want to think about not databases, we want to think, or not data stores or whatever. We want to think about, can I make a programming language that's safe for distribution? Work, I think that's in the similar area is this static analysis technique from Antidote. It's saying, can we apply programming language techniques to a distributed systems problem and solve it there? And there's a group at Purdue that's doing the same thing. And historically, kind of one of the groups that did a lot of work in this area was UC Berkeley a few years ago under Joe Hellerstein. And so, and that those are the people I think that have done it really well in the 2000s. And so, the idea that I think is the idea that I think is so important in the area that I'm working in, and that all of these folks is working on, in is this area that is trying to apply programming language techniques to distributed systems to solve the problems there, because it's not just a database problem anymore. We have these applications that are made up of tens or hundreds or thousands of microservices. How do we know that the application is right? How do we know? How do we test it? Ideally we can have some sort of guarantee. Maybe we can do this through types. And what's interesting about this is that there are so few people working in the field. We need more people working in the field. It's an incredibly important field to work in. And historically, there's been a lot of great work done in the 80s, a lot of great work done towards the end of the 70s into the early 80s, 81, 82. And then there was a lot of work in the mid 80s. And then kind of in the 90s, there was a lull, kind of from the academic side of things, because industry kind of took over with systems like Corba and RMI and stuff like this. Stuff that hasn't really solved the problems in the way that they should be solved. And so I think we're kind of seeing a period right now where a lot of people are getting back into this kind of programming languages, distributed systems area. And so that area I think is really exciting because it can have dramatic effects on the industry if we do it right. If we can, figure out how to, just imagine where we can, have something where we do program slicing or something like this, where we can kind of take a program that's written as a monolith and kind of deploy it as microservices, something like this, and it's type safe and all this stuff, and we know that it's going to work fine because it was correct, and we had some synthesis mechanism or something, or some code extraction mechanism. Like, these are the types of things that I think would really make a big impact on industry, because microservice thing and separating out applications and running different databases and putting data in different databases and duplicating data across databases and building processing pipelines, like, all of this stuff is about moving data between systems. And how do we think about the consistency guarantees that are between those systems? How do we think that the program that is running on a server and a mobile device, how do we know that those programs can communicate? How do we know that the APIs are compatible? Things like this, right? And so all of these things are problems that programming language people like to solve. They like to prove things. They like to know that something is going to be sound. And kind of the systems approach to it so far, and a lot of the approach we take into the industry, is like, we just try to test it as much as possible. And that approach kind of isn't, I think it isn't kind of tenable in the long run, right? I think it's kind of, it's we need to be more principled about solving the problems. And so I think that we need to kind of have this joint work between these two groups. We need to kind of have the systems community and the database community and the PL community come together and kind of focus on solving this practical problem of building distributed applications, because more and more applications today, I would argue that the majority of applications being written today are, whether it's a web browser talking to a server or a mobile app talking to a backend, whether that's AWS Lambda, or this is an actual server running in a data center on physical hardware, like bare metal. These are all distributed applications. And so we really need to alleviate these issues for the programmer.
And given that you're currently working on your PhD and I imagine nearing completion of that program, I'm wondering if you have any thoughts on the projects or industries that you're interested in being involved in once you do reach completion.
When I do finally finish, I will probably try to go the academic route. I will probably try to find some professorship somewhere in this field, because this is kind of where I'd like to continue working. I'd really like to stay focused on this problem of distributed programming, and I think there's a lot of work that needs to happen there. That being said, I do like the tech transfer aspect of it, so I will stay close to industry. I have a lot of connections and friends there, considering I worked in industry for so long. And what we'll probably try to do, and kind of what we're in the process of thinking through now, is figuring out how we can kind of industrialize components, the software artifacts that are coming out of Last But Antidote. So, expect to probably see something on that front soon, from our group. Hopefully, some support, some resources, maybe some sort of open source consortium, something like that. So we're hoping to kind of industrialize these things. So ideally, I think that where at least I think I would be a good fit, when I finish eventually in 2 to 3 years, is kind of in this place where I can at least be involved in research and academia, but be at least close to getting these things into real products used by real people, whether that's open source or something else.
For anybody who wants to follow the work that you're up to and get in touch with you, I'll have you add your preferred contact information to the show notes.
Great.
And as a parting question, to give listeners something to think about, from your perspective, what do you see as the biggest gap in the tooling or technology that's available for data management today?
It's a good question. So from my perspective, I think where I think the biggest gap for kind of this data management problem is today is that application developers spend most of their time in writing like a business logic in their application, writing like coding business logic. And I think one of the problems that bothers me is that, one case I like to think about a lot is a case for kind of eventual consistent, strong, consistent trade-offs, right? So one thing I think about all the time is, if I was let's imagine that I had some application that had to return the result to a user within 100 milliseconds, right? Now, I have to make a request to the database to get some data item, and then I want to return the result to the user. But that user's paying some SLA. Let's say the user's paying to get a response within 100 milliseconds. Let's say this is kind of a soft real-time application, and it has these particular limits. What the application developer would have to write is the application developer would fire off a request to the database. It would set some sort of timer. The application developer would then wait for that timer to fire, and then if the timer fired, they'd like cancel the request and then maybe return a cached copy that's sitting in like a local Redis instance on that machine, or is like memoized or something like this, right? And so from I think it's crazy that the application developer should have to write that. What I would really like to write is there's some value, and I would like to refresh that within 100 milliseconds or return the local copy. Like that is a much more declarative way of writing it. The developer shouldn't have to write this logic to say try to refresh this value. I think that that should be something that's kind of like a primitive, because it seems like a big trade-off that application developers want to make all of the time is they want to make this trade-off to say, can I wait long enough for this thing? Like, I mean, if we could always get the most recent result within, a certain number of milliseconds, we would, right? The problem is that a lot of the time we can't. That's why cap matters. That's why all of this stuff matters. That's why eventual consistency matters. It always comes down to the fact that we can't wait forever. And so I would like to see programming languages, I'd like to see tooling that supports kind of a notion of time, a notion of bounds, a notion of service level agreements. I want to see application code that allows me to say, do this, guarantee this thing is as fresh as possible, but doesn't take longer than 100 milliseconds. And if developers could write code like that, it would be so much more declarative. It would be so less error prone, because it would be provided as a primitive, and then we would be able to do all sorts of things. The runtime could optimize pre-fetching if it knew that instruction was coming up soon. We could, have background processes that try to refresh things at given intervals. Could be some sort of stochastic modeling or something like this. There's all sorts of things we can do once the programming language knows the intent of the programmer. Because right now, if a programmer just says, set this timer and do this thing, the programming language, the runtime, doesn't know what the programmer is actually trying to do. It just knows, oh, there's a timer set and there's some function that's going to fire when it's set, right? And so the more we can build into the language, the better analysis tools we can build, the better runtime support you can build for actually achieving these things really efficiently. And so one of the things that we've done, we've explored as a research direction, at least, is, in a language where operations are annotated, whether they're commutative or not, you can start reordering things at the runtime. You can start optimizing the execution of the program because certain things can happen out of order. But that's only able to be done once you start putting that into the programming language, into the semantics. And so I think, again, I think that's why this field is important. And I think this is an area that's severely lacking that could have a tremendous impact on programmer productivity.
All right. Well, I want to thank you very much for your time. It's been an absolutely fascinating discussion and has given me lots of food for thought, and I'm sure many of my listeners as well. So I thank you for that, and I appreciate your time, and I hope you enjoy the rest of your evening and have a happy new year.
Thanks, you too.